All right. First of all, I'm going to open up questions. What questions do you guys have? You're excited about the homework due tonight? No questions? Okay, I'll go over a little bit something someone asked me about earlier. Let's say you're training a neural network. Before you train, you configure your optimizer, okay? Your optimizer, whatever you call it. Follow a tutorial for how you configure optimizer. And one of the things you do when you create your optimizer is you pass it, whatever the exact kind you're using is, you pass it something that gives it your parameters. Maybe it's model.parameters, open, close parentheses, something like that. But you basically give it your parameters. And given that you have some neural network somewhere, it's got a bunch of weights and biases. So these two neurons and this one all have a bias, not the input layer. Each of these represents a weight. And those are all your parameters. So we have your optimizer has a pointer to where these things are in memory, okay? These are objects, they're PyTorch objects. It knows where they are. Then you have your training loop. Is this already dying? So let's say you have your fbugs, however you want to do your loop, whatever. But you have your fbugs, and then you have your batches. You're going over your batches, and you will have some, let's say, B is your batch, and maybe inside of your batch you have some Y and some X. You don't have to do it this way. This is just one way to do it. So you have your Y and your X. And remember, it's not just one Y value, it's a whole bunch of them. Maybe your batch size is 1,000 or 50. So if it's 50, you have 50 Y values and 50 X vectors. Now I'm repeating all this again and again because neural networks are so important. And the questions you guys ask me make me think I should cover this a lot. So this is for you guys. And you can ask questions as I go. Remember that. So we have this Y and this X now. And our model was already defined before too. You had, some model class above and you instantiated it before, but you have your model. So now we're going to get some predictions. Your predictions equal the model with the X passed through. So if you had 50 in your batch, this is 50 X vectors, and it will give you 50 predictions. Now we need to get the loss. Some people call it a criterion or some loss function or whatever you want to call it. Or you can just write the loss right in here. You can compute the L1 or the L2 loss. You can take the square root of the squared values, whatever it may be. And you're going to put in here the preds and the true Y values. Now, depending on your loss function, you may do it in different orders. Follow the tutorial that you're following, whatever that may be. But you're comparing these two. So that if your predictions are exactly like the Y's, then your loss will be 0, right? But you have this loss, and this is not just a number, it's an object. So the loss is computed with whatever came the output right here. And that has a pointer back to this tensor. And this tensor has a pointer back to this tensor and this one and this one, and all the ones that fed into it. So that with this loss object, I can call the backward function on it. And that automatically tells that loss object to say, you know what, go to this neuron, and if your batch size is 50, I'm going to give it 50 different little corrections. Actually, some of them will cancel each other out, and maybe it averages out to this thing needs to be a little bit higher, like the bias in here needs to be a little bit higher. And then using the chain rule we looked at before, maybe this weight needs to go down a little bit. This needs to go up, and this one needs to go down, and this one needs to go up. And all of these, by the end of the backward function, it's recursively going through here. Every one of these parameters knows which direction and how far the gradient is telling them to go. And remember, the optimizer already knows where all the parameters are. It already has a pointer in memory to all of these objects, and it can modify them directly. Now, if you had a learning rate of 1, and also the optimizer, you also tell it the learning rate, usually. If you had a learning rate of 1, the gradient would be how much change each one of these, but that's too much. So you choose a tiny, tiny learning rate. Nothing in your model actually changes until this step. Step called step. All right, that's easy, right? Right here is the only thing that actually changes the model's weights. Up until then, it was all planning. Even this backward, where you put the gradients everywhere, that's just planning. Step is where it's actually done. And then you redo everything. Now you will also see in PyTorch, maybe there's one in TensorFlow, I can't remember. You'll see a step where it calls something called 0 grad. That just makes the gradient 0. So when you add the new gradients, you're starting over from scratch each batch. That's the right thing to do. It seems to me like something that should be automatically done by now, but it's not. Any questions about that? This is hard stuff, guys. Give yourselves some patience and time. So in the same way we have a training loop for neural networks, we have a training loop for your brain, right? Here's the training loop for my brain that works the best. This is what I do. When there's something I don't understand it, I look at it, I read it, I try to understand it, I think about it, and then I take a nap. Or I just sleep that night and try again tomorrow, and again the next day, and again the next day. And that's so much better than doing nothing for a few days and then trying to get it all in one 2-hour period. Because while you sleep, your brain is changing. It's updating the weights and biases in your actual neurons. It's something else, but you know, it's updating you while you sleep. The first dream cycle is typically very much like experiences you had while you were awake that day. And it's going to be putting you in places and seeing things and feeling things and hearing things that you heard during the day or similar to that. The second or later dream cycles are more about mashups of that plus anything else you've experienced in your life. But all of it serves to help you understand what you were faced with while you were awake. So look at it, think about it, read it, try to understand it. Maybe you fail, that's okay, sleep and try again. Keep doing that. And keep coming to office hours. Let's go over tonight's homework just again. Similar to last week, very similar. But we have 3 sections to the data. And I usually do something like that. The validation thing is new. And remember, here's why we're doing it. Let's pretend we didn't have it at first. Let's pretend we want to train our neural network, okay? But let's pretend we're training it in parallel. We have a whole bunch of them running. And after each batch, or maybe epoch, or tons of batches, there will be a time when you say, you know what? I want to stop and see if there's another model that's better, that I can start from there. And then you go to your models directory, where you've been saving all your models. And you have a bunch of them in there. How do you choose? How do you know which one's better? Well, maybe the first thought you had is, I'm going to, as I'm training, I'm going to be looking at the loss function or the accuracy with respect to the training data set. And maybe I save that. And maybe you can use some registry, a database, whatever, or you can put it in the actual name of the directory that the model file is saved in. These are actually all subdirectories. And let's say you put, you know, accuracy 0.85. And this one has, you know, accuracy 0.86. And you get a bunch of these. Now, if this is from just the training set and you don't consider the rest of the world, you're going to overfit. You will overfit more and more by choosing the one that's better just on the training data set. And if you're not looking at all at anything else, the training accuracy and the test accuracy will begin to diverge. And that's major overfitting, when those two diverge a lot. You want to be able to generalize. So we want some number here that represents goodness, generalized goodness of the model. So then your next idea is, you know what? I'll run it against the test set after each epoch. Get that accuracy. And then that'll be the accuracy I use here. But then that gives you a new problem, because your test set is no longer a measure of your actual generalized accuracy. You've ruined it. You've been cheating in a sense. This is where the validation set comes in. Validation lets you know how you're doing, how good your models are, kind of in a generalized way, while still allowing you to hold out this test set to the very end. That's what this homework is about this week.
overfitting the, or if we're using accuracy based off of the validation set, wouldn't we be overfitting to the validation set then?
Semi, but it's not nearly as bad because you're not using it in training at all. So you never have access to the gradient that would perfect it. You just, every now and then. So you can no longer, by the end of it, after a lot of training, you will have absorbed more information from the validation set. So yes, there is a chance eventually, but it takes many more epochs. Is this hard? It is, but it's worth it, guys. And this is going to be the big, huge technology that you will all need for the next 5 years until something else is invented. And then you'll have to learn that. So this is kind of how things are. You have to keep learning stuff every few years. Your new homework posted today, due next week, is pretty much the same as what you've done this week, but you're all going to do it on one specific data set called MNIST. Maybe one or two of you have already started playing around with this. MNIST is a bunch of small black and white images of handwritten digits between 1 and 10 or 0, 0 and 9. And the idea is that you can recognize the 7 if it looks like that, or if it looks like this, or if it looks like this. That is your homework for next week. And what's nice about this is if we're all working from the same data set, you guys can start comparing strategies, and you can compete with each other in an informal way so you can get the best accuracy. But do just for bragging rights this time, no points, no extra points. Any questions about that? All right. One reminder, when you write your code, I saw at least one person who was still doing this. Data should be outside of the model definition. Don't store your data inside some attributes of the model object. We talked about forward. Shortcuts. The forward function is typically shortcutted by just calling model. We talked about that before a few times. If some of you use the sequential model, I think it typically will create a forward function for you automatically. You don't have to create it. You still might want to create it to give yourself more control. But I think it creates a forward for you. And for all late homeworks, the max I'm going to take off is 50%. So it is still worth it to your grade to finish them all before the night of our last class, which is the finals. All right. Now I want some answers. I'm going to walk around the class. Some answers to this question. And a couple of you have seen this lecture before. That's okay. Feel free to contribute. Give me a definition. It's a word. String is here. Good definition. It's a word. All right. How about a different definition?
Sequence of characters is ascribed.
Okay. What's the meaning?
Some sharing.
What's an understanding?
Consensus.
What's a consensus? Consensus on what?
Agreement.
Agreement on what?
The blessing represents.
What does represent mean?
It's an abstraction of some other concept.
So
Of
this is why the greatest philosophers of the last 100 years spent their whole careers not agreeing and not coming to any real great conclusion, but spinning their wheels and coming up with idea after idea. This is hard stuff. Guys like Ludwig Wittgenstein spent his whole career talking about words and games and what do they mean. Maybe a word has no meaning unless there's two people and they're communicating right now. Is this a word? L-E-A-D. What word is it? Well, choose one. Okay, what word would it be? What does that mean? Another word would be. And what does that mean? Is there another lead? What's the other lead? What's that? In the past tense, right? Yeah. Is that spelled the same? No. So it's probably not this word. But yeah, there, can be confusion sometimes. Can you read the small print? Just a bit of humor. You guys all remember motivational posters from the past, memes? What is a word? Now, if you're not familiar with this, this is pronunciation. Lead, lead. That's not the actual spelling, that's the pronunciation. When we look at what a word is, linguists look at a lot of things. This is how it's written. Here's the part of speech, the pronunciation or phonetic transcription, a gloss or a definition or a sense. So as a computational linguist, you don't have to worry about all the different philosophical games that people have spent hundreds of years talking about. You can just get down to brass tacks and say, can I take off some piece of what this word is and do something mathematical with it? That's the task of natural language processing. Now, what I'm going to impress you with today is the complexity of that problem too, though. And we got to break it down in different ways. Words relate to each other in different ways. Polysemos means it has many meanings. Lead, the or L-E-A-D, those 4 letters, that's polysemos. It can mean different things. We all know what synonyms and antonyms are, right? Have you ever heard of meronyms? Who here has heard of either meronyms or holonyms or hyponyms or hypernyms? Feel free to refer back to this slide later. You guys all have access to it. These are all ways to break down words and see how they relate to each other. And if you're doing things computational with words, this is helpful. Word sense disambiguation is one of the important tasks in NLP. Okay, now this was probably invented by a linguist to play a game. It was probably not a real word, but anyway, autological means the word describes itself. Heterological means this word does not describe itself. Can you guys think of any autological words? Short, very good. How about a heterological word? Very good. It's not actually red unless you write it like this. Right? And then it is. Or how about this? Pronounced red. Is this word autological? After you've looked at it and you've read it, it is, right? Okay. One of my favorite autological words is pentasyllabic. It has 5 syllables. It's pentasyllabic. Monosyllabic is not monosyllabic. So it is therefore heterological. Short and long, you thought of short. Long is heterological. Okay, I'm building up to big question. Yes, go ahead.
Short.
It's not a long word. You're right, it is subjective. You're right, it's subjective. And some words are subjective. I guess you could say, if you were to look at the range that words could be in, is it less than half? Maybe that's it. Who knows? What's the longest word any of you know? Did I hear supercalifragilisticexpialidocious? Anti-disestablishmentarianism. There's probably another one out there. German ones tend to be very long. Okay, I'm building up to a question, but one of the words on this slide. Can any of you think of what question I'm going to ask next? What's that? Yes. But for the other one, well, let's ask that first. Is autological autological? Let's consider the other one. Is heterological heterological? I see a no. Okay, we're going to do votes. Okay. Yes and no. Okay, how many yeses are there? The heterological is heterological. Raise your hand. Okay, you have to raise your hand once. Okay, so no, there's no in betweens. You have to raise your hand once. Okay. Yes, how many yeses? We got 3, 2 yeses, 2 yeses.
It is on. Yes, it's good.
Okay, everyone who didn't raise your hand now. Wow, that's a lot of no's. Okay. Most of the class says no. Okay, so let's take this argument and see where it goes. We're going to say that, well, just call it H, okay? Heterological is not heterological. Therefore, heterological does describe, wait, if it's not heterological, then it must be autological. Let's do it step by step. Heterological is autological. If it's not heterological, it must be autological. Therefore, H does describe itself. Does describe itself. Therefore, H is heterological. So it flips back and forth. Does that remind anybody of anything or any computer scientists you may have talked about in the past? This guy? Kurt Gödel, sorry, my shoe's untied, is one of the smartest men to ever have lived. As computer science majors, you really got to know this guy. His theories are integral to understanding the halting problem, for instance. The main things he's known for is incompleteness. Incompleteness has to do with the halting problem. It has to do possibly with free will, if that exists. I believe it does. I actually have no choice but to believe in free will. Anyway, you guys should know who Kurt Gödel is, okay? This is a very good example of that kind of thing. The easiest example to remember for incompleteness in this kind of linguistic thing is the sentence, same thing happens, flips back and forth. Now, Kurt Gödel's incompleteness basically said that every formal logic system or language, every formal language or formal mathematics will contain within it undecidable propositions. This is one. It's undecidable. It's not true or false. If you say it's true, then it proves it's false. If you say it's false, it proves it's true. Now, if you were to expand on English, come up with new words that could clarify this and resolve the conflict, your new language would have yet other undecidable statements. And Kurt Gödel proved that in the abstract for all languages and all mathematics. That is an achievement. That is a huge achievement. But it applies to language a lot because in language, we try to do natural language understanding. And sometimes you have a question, we want to ascribe truth or falseness to some statements. Maybe it's impossible. You just got to have that flexibility in mind. We're doing on time. Okay. Zeugma is a cool word. A zeugma is a situation where you have some word that plays double duty in a sentence. Okay. You have the question, which of those flights serves breakfast? That makes sense. This flight serves breakfast, that flight doesn't serve breakfast. Which of the flights serve breakfast? Very understandable, normal sentence. Does Air France serve Philadelphia? That's a good question. That question sounds right to the ear. But what about, does Air France serve breakfast and Philadelphia? Sounds wrong. Why does that sound wrong somehow? For you, what do you think? Why does that sound wrong? Yeah. Even though it has the same letters, S-E-R-V-E, you know in your head it's different words, right? So it's different senses. So what your brain is doing here is not working in the space of letters or characters. It's working in some other space. Now, here's a funny thing. Some words are their own antonyms, which is really weird. But again, it's a string of letters. So buckle can mean, to pull together or to fall apart. Something can buckle. You can charge, you can add to, charge your card, or you can charge your battery, which means you're adding to it. To cleave, or you can cleave apart with a cleaver. To enjoin, or you make something fast, or it can go fast. If you hold it fast, that means it's not moving at all. But if it's going fast, it's moving really fast. So what's going on here is there will be two words that in your head they are antonyms. They just happen to be expressed in the same letters on the page. In some other language, they probably won't. So a word may express itself as those 4 letters or 5 letters or whatever, but it's something else entirely. Meaning, define meaning. We talked about this a little bit. Let's take another mathematical example. And maybe this will lead us to something about meaning. For millennia, we were using mathematics. Pretty obvious that the Egyptians had pretty good math when they built the pyramids. Pretty obvious that the Mayans had very good math when their calendar could predict different lunar cycles and, maybe 1,000-year period of iterations of where stars are and stuff. All that math was carried over generation by generation and never rebooted. We just kept adding to it and tweaking it. And then in the late 1800s, math was broken. They had come up with these elaborate proofs where they would show that some weird fraction that was smaller than 1 was actually equal to negative infinity. And they had these stupid proofs that you knew it wasn't true, but there was the proof. So what do you do with that? And that was the time when they started discovering things about number theory. And you've all heard, don't divide by 0, or it's not defined. That comes from the math reboot that happened around 1900, the end of the 1800s. Kurt Gödel was a part of that whole process. George Cantor, Giuseppe Piano, all of these people, their work together restarted math. And one of the things they did is say, let's throw out our intuition and start over from scratch, literally. You have an intuition of what 1 means, and 2, and 3, and 4. Throw it out. We're going to start over, and we're just going to have maybe, a few functions. They call them primitive recursive functions. And 3 was enough to get pretty far. Well, let's just look at 2 of them. First function is the 0 function. Doesn't matter what you put in it, it's always going to give you 0. Now we have a number. We have a thing. We're going to call it 0. That's all it is. It's 0. It's a number. It's the only number we have. Now we're going to define a new function called the successor function. And the successor function gives you something different than what you put in it. That's all we really know. Remember, throw out your intuition. And the successor function, it's going to give us something, and we're going to give it a name. And why don't we call it 1? That's a good idea. And then the successor of 1, I'm going to call it 2. I have an idea. I'm going to call the successor of 2, 3. This will be my new name for this thing. It's distinct from 2. Forget your intuition about it being higher or whatever. It's distinct. It's different. It's able to be disambiguated from. Now, there's also this notion of how many steps. We now have a distance in a sense. The distance between 3 and 1 is the number of times we have to apply the successor function to get there. So 3 equals the successor of the successor of the successor of 0. Now, using this kind of thinking, you can build up all of natural numbers, and then you can do the negatives. And then again, in Cauchy came along and used all this wonderful math to give us real numbers again. So we started to get all the math we had already grown to love over the last 10,000 years. We got it back, but in a stable way that's no longer broken. But this first intuition that they're distinct is something we can apply to meaning. When you have LEAD, that behind the scenes actually has 2 meanings, they are distinct. Forget the intuition of how they relate to each other, whatever. They're just distinct. They're unique. They have a unique identifier in your brain. Some neural activation pattern matches that. When I say the word lead, and when I say the word lead, there are different neurons firing in your head. I don't know what they are. Maybe they're very different for you than me, but I know that they are distinct because you can tell the difference between them. Let's think about these words: cat, dog, tiger, ocelot. Anyone know what an ocelot is? What is it? Like a type of cat. So you can already kind of gather some of these patterns, even though they're all distinct, there is a distance, right? Some are more distant than others, right? So we can't get inside your brains, not cheaply anyway. And we can't look at those neural activation patterns very easily. We can use a functional MRI machine. I've used one of those before. I put my own head in there. Turns out I have no tumors. It's not a tumor, so that's nice. But we need some way in natural language processing to represent these words, to represent the distance between them. Who here has done this before? Representing distance between words. Any of you? Okay. We want to do it in a way that's relatively efficient. Your brain's trying to be efficient. The efficient coding hypothesis means your brain tries to ignore everything it can ignore. If your brain can get away with ignoring something, it will every time. And here's a little example. The character on the left, this is the Cyrillic alphabet. The character on the left is sh. The one on the right is sh or sh, depending on where you are. They're so similar to our ears or the average monolingual person growing up in America. They just sound like the same sound. We have learned to ignore that difference, but babies can hear that difference. And if you grow up in Eastern Europe, you are going to learn this difference. These will be different to you. But in the space of English, this difference, even though the sound file still has a difference, your brain collapses it, or it ignores that part of the signal. Your brain is doing dimensionality reduction. We talked about that with UMAP, with PCA, principal components analysis. It's very important to ignore what you can ignore when you're doing machine learning. We use vectors to represent meaning or represent a word in general. And let's pretend we're dealing with just words that have only one meaning, okay? For now. Dog actually has many, many meanings. There are verbs for dog, which is just the noun, the most obvious definition. Does this setup basically match your intuition? cat, ocelot, tiger, they're pretty similar. They're different from each other, but they're pretty similar. And they're definitely different from dog. If gorilla was on here, you would probably be, over here somewhere. Something like this is what we try to do for all words in a language. Try to vectorize them in space where the ones that are different are distinct. And there's a distance metric. The ones that should be further are further. The ones that should be closer are closer. And once we've done that, we've done our job. This is not exactly how your brain does it, obviously. We're maybe never going to get there exactly how your brain does it. But this is a way that's faithful to how you view the world. At least we tried for that fidelity. Okay. This word, what does this word make you think of? Throw out some other words that you think are related to this word. Okay, give me one word. That might be related to this. Spicy. Good. You.
Austin.
What?
Austin.
Boston?
Pasta.
Oh, pasta. Very good. Are you?
Boy.
Boy? Okay, very good. How about you? Very good. Pots? Very good. All right. This word was beloved by Shakespeare. He used it a lot. Look at the other words that appear near and around saucy. We got lackey, knave, stranger, beastly, jives, querulous, weasel, blunt, envious, barking. One of the first ways that NLP experts were able to model words was by their friends. You are who you hang out with. So they would see what are the words that appear in the same sentences as a word. And that is a first draft model for representing a word. So let's say we did this for a giant body of text, maybe just all of Shakespeare. We've had all the words of Shakespeare, and we want to represent saucy. First of all, we need a vector of some kind. That vector is going to have an element for every word that appears at least once in Shakespeare, or maybe you can say appears at least 10 times. So maybe the word the will be the one that appears the most. And then you have a, and then a whole bunch of others. And maybe down here you get to, envious. And then you get to jives. Anyway, you get the point that there's a vector that you can generate where every element references one of these words. Now, let's take the envious barking of your saucy tongue. Good. Barking too. So we have that one sentence at the bottom. That's our first example. We're going to say we are creating the vector that represents saucy. Well, we're going to add 1 to the value, 1 to the envious value, 1 to the barking, and 1 to the other words, but let's say they're in here somewhere. And then we go to some other sentence, I will speak to him like a saucy lackey, and under that have it, play the knave with him. So we go through again, and we add a value to each of these, depending on what words we see that saucy appeared with. And in the end, after we go through the entire body of Shakespeare, we will end up with a bunch of counts along here. But let's say we do that for every word all at the same time. So as we go through this one sentence, we're adding to those counts for the vector for saucy, but also the vector for the and envious and barking, of, your, and tongue. So if there's maybe 5,000 words that appear at least once in Shakespeare, then you end up with a 5,000 length vector, and you end up with 5,000 of them. Make sense?
So you're counting each time a word is in a sentence. For saucy, each time a word is in a sentence for saucy, you're counting.
Counting how many times other words appear with it. Right. So when I'm doing the vector for saucy, somewhere in here, there's a field for saucy. I'm leaving that blank.
So when you make a vector of another word.
Yes. Okay. Yeah. When I make the vector for barking, then I add one to the saucy field. Is there any way we can make this better?
The order, like appending the order of words is cool.
Very good. That's a very good idea. Especially in English, word order is very important. How would you represent that?
If it comes before a noun, that's an important one.
What number would I put instead of this number? Okay, we'll get there. It won't be today. What about this word? Am I really getting a lot of information? How much information would it be getting? Is there a way to compute information? Have we talked about that at all in this course? Who can remind me? How do we compute information? Yes, it's part of entropy, right? Just the log p part. And what you'll find is that the information value of the is almost 0. And it gets better and better and better. But there's also words that appear so infrequently, they're not useful either. Because they're useful in only 0.1 of all examples. So it's a waste of your computational resources to pay attention to them. So we came up with TF, IDF, term frequency, but that's not the only thing. You also got to pay attention to inverse document frequency, TF, IDF. I'll never forget the day I didn't get a certain job because they asked me what TF, IDF was on the interview, and I didn't know. After that interview, I will know forever. Term frequency. How frequent is the term? The is too frequent. So we're going to cut things off and ignore them if they're too frequent. Maybe if they appear in above 0.8 of all sentences, totally ignore them. You can choose different values. Some people choose 0.7 or whatever. Inverse document frequency. So how many times they appear in the entire corpus of Shakespeare, for instance. And if you have some strange word, that only appears, if you normalize all the appearances, and this thing only appears 0.0001. Normalizing, remember what normalizing means? So if we take all these counts and we divide by the count of the highest one, which may be the word the, and let's say a word only appears, this much, that's its document frequency. You can take the inverse of that and get 1 over that basically. But typically inverse document frequency is how we like to think about it. And you want to only choose things that are above a certain frequency in the entire corpus. So we're gonna ignore the and we're going to ignore the really rare ones too. And that's it for class today. Any last questions? Thank you, everybody. See you next time.